What's up, guys? We are starting chapter 14, which is, well, the whole year's been, not the whole year, but recently we've been doing quadratic functions. And chapter 14, we are looking at basically all different kinds of functions. So first is exponential functions, which we did last year. We're just going to look at them, give us a little review, maybe go a little bit more in depth with these. So here we go. Okay, so this one says f and g are exponential functions with the same base. Is the graph of g a compression, a reflection, or a translation? Okay, so since they have the same base, we know they're the same shape. So they're both going up at the same rate, basically. And this, if you look at it, it could be a translation because g could be shifted to the right of f, but it also could be a compression or not a vertical translation, but it could be a compression also. Definitely not a reflection. So either a translation or possibly a compression, which just means that it's stretching it or shrinking it. Okay. So it says you can apply the four types of transformations: stretches, compressions, reflections, and translations to exponential functions. The factor a in y equals a times b to the x can stretch or compress and possibly reflect the graph of the parent function y equals b to the x. The graphs y equals 2 to the x, which is red, and y equals 3 times 2 to the x in blue are shown. Each y value of y equals 3 times 2 to the x is 3 times the corresponding y value for y equals 2 to the x. So that's an example of a stretch because it's basically stretched that red function up, stretch it 3 times the size. So we say that is a vertical stretch by a factor of 3. Okay, and that's going to be the case whenever there is a multiplication in front of your base function. Okay, so if we look at this one, how does the graph of y equals negative 1/3 times 3 to the x compare to the graph of the parent function? So this should be a compression actually because it's a 1/3 here. So instead of getting stretching up, I guess, it's going to compress down. So let's say that your original function looks like this. The compressed function would look, everything would be 1/3 the original height. So it looks something like this. Okay, then we also have this negative right here, which is going to take that purple function, it's going to flip it, reflect it over the x-axis. So it actually, in the end, looks something like this. Okay, obviously these are just approximations, but you can always make a table of values and figure out where the points go specifically, making like an xy table and plugging in your x's and y's. But that's what it should look like. So it is compressed by a factor of 1/3, and it is reflected over the y or the x-axis. So it's a vertical reflection. If the function looked like this, y equals 1/3 times 3 to the negative x, because the negative is up with the x, that would be a horizontal reflection. So it would reflect over the x or the y-axis. So whenever there's a negative, if it's with the x, it's a horizontal reflection over the y-axis. If it is in front, then it is over the x-axis, and it's vertical. Okay, a horizontal shift, y equals a times b to the x minus h, is the same as a vertical stretch or compression. Yeah, that's kind of what we were talking about earlier. Y equals a times b to the negative h times b to the x. Vertical shift, y equals a times b to the x plus k, also shifts the horizontal asymptote from y equals 0 to y equals k. Yeah, so don't forget that with exponential functions you have a asymptote, which is the imaginary line that it never crosses. And it starts at y equals 0, so the x-axis, and then it shifts to whatever the vertical shift is. For that other part, it's saying that this could also be, because you can rewrite this right here as 2 to the x times 2 to the negative 4. And that works with exponentials because of the properties of exponents. Because these have the same base, you would just add the exponents together. So really, you could think of this as a horizontal shift because it's adding and subtracting with the x. Or you could think of it as, this would be what, 1/16 times 2 to the x. You could think of it as a compression. Yeah, so this would be shifting right 4 because it's always opposite when it's with the x. So it's shifting right 4, or you could say that it's vertically compressed by a factor of 1/16. Okay, obviously this one's going to be easier to think about, so it's probably the best one to go with. The next one, this one, we have this 20 right here. So that's going to be a vertical stretch. This 1/2 doesn't really matter. That's just the base of your function, so that's not really a transformation. So this one's vertically stretched by 20, a factor of 20, and then this plus 10 is a vertical shift up 10. And because that shifts vertically, your asymptote also shifts. So your asymptote would be up here at 10. I use a dashed line. And then it looks, well, it's actually a 1/2, so it's actually coming down like this. But it's not supposed to cross that. Whoops. But then it's stretched by 20, so it's actually probably steeper than that. It's more like something like that. Okay. And the reason I'm going down this time instead of up, or like this, is because this is a fraction less than 1 here. So if you think about this, 1/2 to the x, this can also be written as 2 to the negative x, because a negative exponent makes a fraction. So that's why it's being reflected over the y-axis, yes, because it's a negative. So when it's a fraction or a negative exponent, it comes down, it's decreasing. When it is a positive number, like 2, it's going up like that. Okay. Onward we go. Okay, so in summary, for exponential functions, you have a stretch when a is greater than 1, the absolute value of a, because the negative is a reflection. But you have a compression when a is a fraction, less than 1. You have a reflection if a is negative, and the a we're talking about is this guy right here. You have translations, horizontal if it's up with the x, and the vertical if it's out to the end with plus k, and then all of them combined would look something like this. That's the general form of the function. Okay, whoops, whoa, what's going on? Okay, so now let's look at a couple more problems. So sometimes you can rewrite exponential functions to reveal information about the situation of models. Yes, okay. I didn't want to do that. Oops. Oops. Why can't I make it? Never mind, okay. Okay. So this is the function p equals 80 times 1.25 to the d, models the population of a city in thousands after d decades. What exponential function models the population after t years? So basically we need to change decades into years. So the first thing we need to know is how many years are in a decade. Well, 10 years is equal to 1 decade. So a common misconception that people do is they want to write 10y equals 1d, which does not work because if you plug in like 30 years, that would go into y. If I plug in 30 here, 10 times 30 is 300. 30 years is not 300 decades. So we actually need to switch those. So what we want to say is 10 times d equals 1y. That way when you plug in a number like 10, so 10 years, that's not working. Anyway, yeah, if you plug in 10 for y, then we get 10d equals 10, and then you solve for d equals 1. So 1 decade is the same as 10 years. So that's what we want to do here. We want to look at this equation, y equals 10d. And then, because we have d here, we actually need to solve for d. So we're going to divide by 10, so we get d equals y over 10. So decades, number of decades equals numbers of years divided by 10. So if I have 60 years, divide that by 10, we get 6 decades. So that's what we want to plug in here. Y over 10. So let's write some stuff. So your new exponential equation would be p equals 80 times 1.25. The only thing that changes is d would change to y over 10. So now we're looking at years instead of decades. Okay, so that would be the exponential equation. And then it doesn't quite look the same because it has that divided by 10. So because of the laws of exponents, what we can do is we can actually write this as p equals 80 times 1.25. This y divided by 10 is the same as y times 1/10. So what we can do is we can move that 1/10 to the inside of the parenthesis, like so, and then the y out here. Then we just have our variable on the outside like that. And then we can simplify a little bit. So 80, let's figure out what 1.25 to the 10th is. So I get 1.0, this is a really long decimal, 0.2257 if we round it to the y. So basically if we look at, this would be our new exponential equation, but if you look at your original function here, this is saying that your initial value is 80, so you start with 80,000 for your population, and this in here is your growth rate, your growth factor. So that's saying that it's growing at a rate of 25% per decade. Okay, 25% because 1.25, you have your 100% from the 1 plus 25%, which is this decimal right here. So we don't include the 100% in your growth rate, we're just looking at the 25%. So it's growing 25% each decade. So if we want to look at years, what is your yearly growth or annual growth rate? What we want to do is we want to look at now with the yearly equation. Your yearly growth rate is this right here. So move our decimal twice, 2.257%. Okay, so you can see that even though it grows at 25% per decade, we can't just divide that by 10, because if you do that, you'd get 2.5%, which is a little bit of an overestimate. And that's because this is an exponential function, not a linear function, so you can't just divide by 10 and keep it constant. So that's why we have to rewrite it like this to find the annual growth rate. Okay. All right, next. Okay, up to this point you work with rational bases, meaning bases that are fractions or whole numbers. However, exponential functions can have irrational bases. One important irrational base is the number e. The graph of y equals 1 plus 1 over x to the x has an asymptote at y equals e, or 2.71828, yada yada yada. If you look at this equation up here, this looks a lot like our compound interest equation, which is a equals p times 1 plus r over n to the nt. So basically if you just change those n's to x's, it's very similar to compound interest, which is important when we're doing continual interest, because this n right here, what that means is that's the number of times per year your account is compounded, your interest is compounded. So if it's a annual compound, that means it's compounded once per year. If it's compounded monthly, that means it's 12 times per year, so this would be 12 and then 12 up here. So that's essentially what these numbers are right here in this equation. Natural base exponential functions are exponential functions with base e, so it looks like e to the x or something like that. These are useful for describing continuous growth, so that would be a continuous interest rate, if we're looking at the interest right here, or decay. Exponential functions with base e have the same properties as other exponential functions. How can you use a graphing calculator to evaluate e to the third? Well, you can type it in, because your graphing calculator should have an e button, but you can also graph it, and you would get, so if you graph y equals e to the x, and then just go to the table and figure out when x is 3, that would work too, but you can just type in e to the third as well. It is somewhere on your graphing calculator, probably by the log, near the log button maybe, or maybe near the exponent button. It's probably like one of the second menu buttons. Okay, but that does bring us to compound interest, which is why I was bringing up compound interest earlier. There is what we call continuously compounded interest, which means that your interest is compounding basically instantaneously. And the formula for that, it's a little bit simpler formula. It's A equals P times E to the RT, and A is your amount in the account at time t, so basically your balance. P is the principal, or the initial amount. E is just that 2.1828, something like that. And then T is time in years. E is your annual interest rate expressed as a decimal. So that's how we can calculate continuously compounded interest. So looking at this one, it says, suppose you won a contest at the start of 5th grade that deposited $3,000 into an account that pays 5% annual interest compounded continuously. How much will you have in the account when you enter high school 4 years later? So we have all the information here. A is what we're looking for. Our principal would be the 3,000 times E. Remember, E is not a variable; it's actually a number, like pi. Your interest rate would be 5%, so 0.05 times T, which is 4 years later. And then you can just type that in your calculator. And what do we get? So I got 3,664.21. Whenever you're working with money, you always want to round to the nearest cent. Okay, so this is actually the most money that you could earn with a 5% account without having deposited any more money. So continuously compounded interest, that is the best interest you can earn, I guess. The more times the interest is compounded, the more money your interest earns on itself. So being continuously compounded is obviously the best that you can do, because it's basically infinitely compounded. Okay, that is all, I believe, for this lesson. It is. So that is a little bit more about exponential functions, a little bit of review as well. So make sure that you guys do the Canvas quiz and the Math Excel. Don't forget about the Math Excel. And get on Zoom on Thursday, because I haven't seen you guys in a minute. So yeah, Thursday at 11:30. See you there. Okay, bye.